This is the golden eye of the James Webb Space Telescope. Unparalleled in scope and scale, Webb is the largest telescope to ever launch into space.
It's a little bit like our generation's Apollo in that it was very challenging to build, but the payoff is also very large. I mean, this is about as powerful as it gets.
This is an extremely ambitious project. We developed all these new technologies that didn't even exist, but we needed it to carry out the science.
An international project like this that has countless firsts takes time, but the painstaking effort to design, construct, and test Webb's optical system will be worth the wait. Overnight, the eye of the telescope will revolutionize our understanding of the cosmos and be set loose on the biggest questions in astronomy.
Well, I've been working on the James Webb Space Telescope for 20 years. And when I first started, we really didn't even know exactly what the design would look like, what materials we would make the mirrors out of, how many segments the telescope would be. We actually had to invent multiple technologies.
That's because the astronomical community was after something that had never been observed before: the early universe. The first stars and galaxies started to form 100 to 250 million years after the Big Bang, around 13.6 billion years ago.
Because the universe is expanding, the visible light from the early universe gets stretched into the infrared, and that's called a cosmological redshift.
It's this cosmological redshift that Webb's optics will be hunting for, to uncover the story of the early universe.
Infrared light can pass through dust in the universe, and so it allows us to peer through dust clouds and see, for example, stellar nurseries.
No other telescope today has the collecting power and sensitivity that NASA's JWST has to lift the veil on the universe's secrets.
The James Webb Space Telescope is sensitive enough that if there were a bumblebee at the distance of the moon, we would be able to detect it.
The telescope's core superpowers come from its advanced optical system. James Webb's eye, otherwise known as the optical telescope element, consists of 4 ultra-reflective golden mirrors and dozens of subsystems to support the massive optics.
The first thing you recognize is the gold mirrors. There is a reason why we chose gold, is because it has a very high reflectivity in the infrared.
Out of the 4 mirrors, it's the primary one that really stands out.
That's the first mirror that light hits. And in this case, we have 18 segments. They're hexagonal shaped.
Which means each mirror actually acts as a separate telescope until they're aligned in space to work as one. All of the 18 hexagonal segments and additional mirrors are made of beryllium, a strong and lightweight metal that holds its shape at cryogenic temperatures. Remember, space is a balmy -270 degrees Celsius.
The other subtlety of it all is because it's infrared, the mirrors have to be cooled to very cold temperatures so that they don't produce heat in the form of infrared light that would contaminate the images. And lastly, a large telescope gives you resolution. The resolution goes with the diameter of the primary mirror.
Webb's primary mirror is 6.5 meters in diameter, which gives the telescope more than 6 times the collecting area of the Hubble Space Telescope.
It's a lot like collecting raindrops, and the bigger the bucket, the more raindrops you collect. And when you're trying to see the very early universe, which is very dim, you need to collect a lot of photons.
For the engineering team, it's easier to look back at what was achieved when you're at the finish line. So many aspects of the telescope needed to be invented before manufacturing began years ago, from the segmented beryllium mirrors to the large sun shield for keeping the system cold, to algorithms. Lots and lots of brand new algorithms for keeping the mirrors aligned 1.5 million kilometers away.
In terms of, a science mission like this is the largest, most ambitious one that NASA has ever taken on, and it's arguably one of the most complicated but also powerful ones.
That's because to see the universe like never before, it requires a new type of observatory. For the JWST team, building that observatory meant constructing a complex cascade of mirrors that can focus light down like no other telescope before it.
The first mirror is the primary mirror. That's what initially collects the light from the distant universe. The light then converges down to a secondary mirror, and the secondary mirror continues to focus the light, and then that reflects light to what we call the tertiary mirror. And then finally, the light is sent to a fourth mirror, which is the fine steering mirror. And the purpose of that mirror really is to correct slow drifts between the telescope and the spacecraft.
After all that, an image is created as the light enters the 4 science instruments.
We call them science instruments, but you can think of them as cameras. They each have their own detector, which actually collects the light, like the detector on your camera. The light photons get converted into electrons. They get recorded onto a data recorder on the telescope. And then the data actually gets sent back down to the Earth using the deep space network.
And once we have the first completed images, the long wait will have ended.
So space telescopes are like time machines. In a sense, they can take us back and collect these photons that were created at the very beginning of the universe.
That light is always there. It's always coming down, we just haven't had the capability until now. In the first year of operations, Webb's mirrors will collect light from early galaxies and stars, the environment around black holes, supernovae, and other space phenomena with greater sensitivity than ever before. And of all the highly anticipated observations, one is a personal favorite for Michael.
I'm really excited about the exoplanet discoveries. We know of over 4,000 exoplanets orbiting other stars, but we don't really have an understanding of what their compositions are, and that's one of the key aspects of the Webb mission. For the first time, we'll really get a good understanding of their properties, and those are very fundamental features for understanding how they formed, how they evolved, and also will give us some insight as to the habitability of these exoplanets, whether there might be liquid water where life could exist.
By searching for the building blocks of life elsewhere, it can give us insight into how life began on our own pale blue dot. Webb's science mission touches on so many fundamental questions in cosmology that it holds the promise of rewriting and expanding our textbooks for years to come.
So every time we have a transformative increase in observing capability like Webb, there's just tremendous scientific discovery.
We used to use the phrase early when we were developing Hubble, expect the unexpected. And I think here you can almost say expect the unexpected squared. The James Webb Space Telescope is a new kind of telescope. It's never been done before. This is really new terrain for NASA and for the world, and setting a stage for future telescopes that are scalable to larger sizes.
Which means if we ever want to see a pale blue dot around another star, the foundation has been set.